Hello students, welcome to the channel Statistica Hub. So this is our lecture number 6 on the course SH201A. Okay, so till now we have covered some basic introduction about probability. We covered something like what is probability, how the probability is being measured, and different definitions of the probability. Then we went over like the basic concepts like the axiomatic probability, the conditional probabilities, and the total probability theorem, and the Bayes theorem. Okay. Now moving to the next chapter in this particular course, we are having the chapter that is the random variable. Okay. So this random variable, this is like a very nice chapter, and we have to understand like a lot more about random variables because the complete statistical courses that we are going to take up, like in different colleges or maybe different courses that you are taking, the random variable it will be playing a very vital role in all the different courses. Okay. So let's try to understand what is a random variable. So this is again a first lecture in this particular topic. So this will be very introduction about the random variables. Let's see how this particular topic comes up. Okay. Before moving to the random variable, we have to introduce something that is known as sigma algebra. Okay. These are some of the topics that we cover in measure theory. The students who are like in some university or something, university means to say like in their master's course, they will be having something about measure probability rules or maybe measure probability theory. So in that one, you are going to cover these type of things. So I will not be going like very deep into that particular topic, but some basic introduction about the same terms. Okay. So if you move back to like maybe I think the fourth lecture, we have introduced something about the probability space. If you remember S, B, P. In that one, I told you one thing that this B, that is your sigma algebra, if you remember. Okay, so what is the sigma algebra? Let's try to recap the same thing. Then we'll be moving ahead towards the like the random variable. Okay, so if I just introduce like what is the meaning of sigma algebra? Okay, so we will write the definition first. So a sigma algebra. Let's say the sigma algebra to be some f. Okay, this is some sigma algebra. This is defined on omega, the sample space. It is just a collection of, it is a collection of subsets of omega. Subsets of omega. Okay. Now the point is you can have different subsets. If I say we are having some particular set, let's say we are having some set omega, and in this set we are having some elements. Let's say the number of elements is n. So the possible number of subsets in this particular set that will be possible to be 2 raised to the power n, correct? Now the point is someone can make like various subsets. Someone can say, sir, my subset is containing maybe the first element, second element, third element, and so on. You may define different subsets for a same set. Okay. Now the point is which particular subset they are considered to be the sigma algebra. We have to understand that particular point. So it is a collection of subset such that it satisfy some conditions. Okay, and what are the conditions that we have to take into consideration? So the first condition that we have to take is this omega, this must belong to the F, the sigma algebra. Okay, moving ahead, the second property that if there is some element A, if that is belonging to F, then the A complement, this must belong to the F. Okay, that means to say you can simply say it is closed under complementation. Okay, so from the second property, I can see one thing that this implies that this phi that will be belonging to the F. Because under the first condition, the omega that is belonging in the F. So the complement will be phi and that must be belonging to the F. Moving to the third condition, so that says that if you are having some element AI, I can be like 1, it can go till infinity. Okay, that means to say we are having some A1, A2, A3, and so on, some A infinity. If they are subset of F, or you can say if they are belonging in the F, okay, just keep this belonging to the F, then their union I running from 1 to infinity, AI that must belong to the F. This particular property is known as uh, closed under countable unions. So if any particular kind of subset of the omega, if that is following these three properties, then that particular subset is known as your sigma algebra. Okay, I hope that makes sense. Okay, moving ahead, then we are having something that is known as the measure. Okay, so what's a measure? Let's try to have a look on this part. Okay, so technically a measure is defined on the sigma algebra. Okay, so moving ahead, so a measure is defined on a measure is defined on the sigma algebra. Okay, and technically it is some sort of function. Okay, what does that mean? And it is a function. So if it is a function, it must be having some domain, it must be having some range. So we are saying that it is defined on the sigma algebra. So if it is a function, let's say we are having, let's say the measure to be some mu. So if mu is my measure, so mu that will be defined on F, the sigma algebra, that is the domain, and it will be taking values in 0 to infinity. So that's how a measure is defined. Okay. Again, if it is a measure, it must be like you can define any function, but there must be some particular properties that a particular measure or that kind of function that must satisfy. So it must be satisfying. It must satisfy certain properties. Okay. So the first property says that if you take the measure of the empty set, the null set, that must be coming out to be zero. Okay. The second kind of property that it must be satisfying is the if you are having some AI, again the similar kind of property, I going from 1 to infinity. If these are disjoint sets in the sigma algebra, then the measure of this mu, that is the measure. So the measure of union I running from 1 to infinity AI, that must be equal to summation I running from 1 to infinity mu AI. Okay. So these two conditions must be satisfied by the measure. Then we are going to say that this particular function that is denoted as a measure, or it can be called a measure. Okay. This particular property, the second property that we just wrote, that is known as countable additivity. Now you can simply compare this particular property or these properties in the context of like the axiomatic probability. What does that mean? So if you take into consideration the axiomatic probability, that is also some sort of like measure. Like in the very basic terms, we don't define the concept of measure, but as we are covering up the very introduction about the random variables and taking up the measure theory also. So that's how we can define the measure. So if I go for the third topic, technically the introduction. So we are having the probability measure. Okay. Now we just came to know that we are defining some particular function that is defined on the sigma algebra, and that must be satisfying these kind of properties. Then I said that this particular property that is being held in the case of axiomatic probability also. You just try to see like how that particular concept is like inclined with the axiomatic probability. So if I go for like SBP, in spite of SBP, if I just try to equate that by omega FP. Now I am saying that this is my sample space, this is my sigma algebra, and this is the probability. So this probability function, as we covered earlier, this is some sort of function. Now this function is known as a probability measure. Now, if this is a probability measure, again the similar kind of properties will be there. So this P is defined on the sigma algebra, that is my F, okay, such that the same properties that you already covered up, we are having like the probability of phi that must be equal to 1. Correct? So again, we are having the axiomatic definition. So it will be following these particular properties. So the properties of the probability function that come up like this. The probability of any event that must be in between 0 and 1, both inclusive. If A belonging to the sigma algebra. Okay. Moving ahead, the second property that we already wrote over here, probability omega, that will be equal to 1. And the third property, the countably additive. So P is countably additive. So that's how we define the concept of the probability measure, the basic measure-theoretic rules, and some basic idea. Okay, we covered the similar kind of thing in the previous chapters also, but that was something like very, very precise. Now in this one, I try to explain little bit more in some more advanced version, maybe in some more explanatory version. Okay, now let's try to come to the concept of random variable. Now the point is, if you go for the random variable, this is like a very vast concept. I will not be going like very deep into this particular part, not coming into the Borel set or something. We're going to cover like from the very basic introduction, very basic kind of thing, like how do we define a random variable? Okay, coming to this part, we are having the concept of random variable. So what is a random variable? Okay, think a little bit. Like whoever read like any particular book, then you must be knowing like what is a random variable. So like from the old days when I was a kid, I was a student. So I was not very good in studies. So I just like, okay, read something, then just ignore everything. So during one of my viva, my teacher asked me, Rahul, please explain me what is a random variable. Okay, as a dumb kid, I just gave her the answer, ma'am, it is a variable that is random. Okay, so technically that was like very, very inappropriate definition. And my teacher said that, okay, this is something that is like completely incorrect. So just go and read again. So at that particular point of time, I try to just understand a little bit more about the concepts and I try to focus like what is the meaning of everything. So from now onwards, like we are going for like more advanced kind of thing, more understanding kind of thing. So let's come to the point of random variable. So first of all, you have to understand it in like step-by-step format. So it is some sort of function. Okay. So if it is a function, it must be containing some sort of domain. It must be having some sort of range. Okay. So if you say we are having some random variable, then the random variable is a function and it is a function from the sample space to the real line or real number. So technically random variable is a real valued function, real valued function defined on the sample space. Okay. Now coming to this particular concept, now the point is like in the book you may have heard or you may have seen these kind of notation. They say x is some random variable and x can take value maybe 0, 1, 2, 3. Possible thing like one kind of example. Okay. Now what is the meaning of this particular notation? So we will try to understand what is the meaning of this notation. So let's move ahead. So if I take up like, for the sample space, like we are defining the random variable on the sample space. And how we are getting the sample space? So the sample space is defined according to some random experiment. So first we have to take into consideration what is a random variable, random experiment. So I hope you remember like from the earlier chapters, what is a random experiment? So random experiment is an experiment with at least two outcomes. At least two outcomes which are predefined, which are predefined, but we don't know, but we don't know what will be the what will be the final outcome. Correct? So that is the idea of a random experiment. So for the random experiment, you define the sample space. So we are having the sample space S, that is the collection of all the possible outcomes, collection of all the possible outcomes of a random experiment. Now the point is, I will try to introduce you to like how we are denoting the random variables in the context of like random experiment and everything. So let's try to take up this one example. So if you say you are having the experiment, in this experiment, I am tossing up a coin. So if you toss up a coin, then we know the possible outcome, the sample space that will be head, comma, tail. Correct? Okay. Now I told you this random variable x, that is some sort of function defined on the sample space, taking some values in the real number. Okay. So now this particular function x, technically, if I try to just use some more mathematical concepts or maybe some mathematical notation that you may have encountered like in the earlier classes, maybe 9, 10th, 11, 12. In those grades, you must have covered something. You just say y, that is some function of x. In this notation, this is some function. You introduce the variable x and you'll be getting the value of this function at the value x and you'll be getting a value of y. So in the book, when they say this x random variable, this is taking some particular values. So technically this x, that is some sort of function. So it is some function that is working on something and you are going to get the final value. The final value, that will be some real number that we just covered. Okay. So in this particular example, if I say my x random variable that counts number of head. So in this particular part, when I say x, you can take like the sample space s, that is in this part h comma t. So you will be getting h in this place. Okay, in this function, you'll be getting an output that is coming out to be 1. You get x, you introduce t, you'll be getting a value 0. So that's how a random variable is defined. So generally, the notation for this one, that is x is some function, you are having some omega. This is some random variable. And in this random variable, this x omega, this complete term, that will belong to the real number. And this omega, that will belong to the sample space. Or you can just say x. So that's how we introduce, or we just go for the definition of the random variable. You can take another example. Let's say you are having, like the experiment is something like this. You're tossing up 2 coins. So in this case, the sample space that will be covering up head, head. Okay, it must be like head, head. No, that's correct. Okay, it will be head, head. It will be head, tail. It will be tail, head. It will be tail, tail. Correct? Now, again, I'm saying the x that says count the number of head. This counts number of head. So again, in this x, you are going to introduce h. You'll be getting a value 2. You'll be getting x, ht. You'll be getting a value 1. We go for x, th. You'll be getting a value 1. You get x, et. You'll be getting a value 0. So that's how we denote the random variable. Again, you can see x omega. That is my random variable. And we are having x omega that belong to the real number, while the omega that belonging to the sample space. Okay. Now there is one more concept that we can take through in this particular chapter only, or in this particular lecture only. So we are having support of a random variable. Support of a random variable. So technically support is the set of all the possible values of a random variable. In other sense, you can simply say like, or we can simply say support of any random variable. Support of any random variable is just its range. Like a random variable is a function, so it will be taking certain values. So it will be taking some values in the real numbers. So if you get the range set, then this range set is known as support of that particular random variable. So that's how we introduce the random variable. So random variable is a real valued function that is defined on the sample space. This is the takeaway from this particular lecture. I hope you're able to understand what is the meaning of random variable and some basic concepts about the signal algebra and something about the measure theory, the probability measure. Okay, that was all about in this lecture number 6. In the coming lecture, we are going to introduce more about the different type of random variable and the PDF, PMF, those kind of things. So stay tuned. Thanks.